Again, everybody, welcome to day 3 of Too Hot to Test. We have a number of very interesting presentations from very knowledgeable folks. First one being Weihua Tang of Intel. Weihua manages a research and development engineering team that specializes in thermal and fluids competency. This includes focus on packaged thermal technologies, thermal modeling methodology, and fundamental understanding of semiconductor substrate packaging, assembly, and test process, covering a broad range of product segments. She has 10 plus years of experience in the semiconductor industry. She is the associate editor of IEEE Transactions on Components, Packaging, and Manufacturing Technology, and a contributor to IEEE HIR Thermal Technical Working Group. Please go ahead, Weihua.
Thank you, Rob, for your introduction, and thank you to the audience for your interest. I would like to thank my colleagues, Ravi, Rajiv, and Abram at Intel Corporation for their contribution to this presentation. And also, this presentation combines the updates from Heterogeneous Integration Roadmap, Thermo-Technical Working Group. Like to thank you, Madhu, for sharing his slides. So I will touch base on those updates towards the end of the presentation. So I will start with an overview of the evolution of electronic packaging with a focus on advanced packaging technologies and the associated thermal challenges this technology brings. And then I move on to look at from a high level, how do we addressing those thermals at silicon, packaging, and system level. And finally, I will wrap it up with a list of call to action items. So if you look at today, the diversity of connected devices, the number of connected devices has grown exponentially. And then there's a very broad spectrum of devices, packaging, and form factors. Let me bring the laser point. So they cover like computing, smartphone, digital home devices, wearables industry, automobile industry, network infrastructure, and data center / cloud. For thermal engineers, we are particularly interested in the power consumption and the cooling solution and system boundary conditions. If you look at the device design power, they can vary from a few watts for like small smart gadgets to easily several hundred watts for processors used in data center. And then cooling solution and system boundary conditions are also quite different and diverse to meet the user condition and also meet the product's reliability requirement. Some of the devices will be used in well-controlled environment, like data center. Some of them will be used in, for example, 5G towers. They will be no active control, thermal control, rely on ambient environment cool and giving the quite different different geolocations. It could be hot space, it could be very cold area. How do we design our thermal solutions to meet all those product needs is quite challenging. So to meet those product needs, the packaging technology has evolved significantly, driven by silicon scaling, I/O density, and heterogeneous integration. This is the packaging technology roadmap released by Intel at Architecture Day 2020. The key scaling matrix we are looking at are interconnect density, power efficiency, and scalability. I will start with the first two metrics. So this is a standard package. Compared to standard package, EMIB offer a cost-effective approach to increase the interconnect density and power efficiency for 2.5D integration. When it comes to 3D stacking, Foros provides the dense vertical connection among chiplets through 3D face-to-face die-to-wafer bonding. it is nice technology because it can see the footprint. It can minimize the footprint of the package area by 3D stacking active IPs. But with that, it comes significant thermal challenges, especially when you're trying to vertically align IPs with dense power density. And then this effectively will increase your power density over the same silicon footprint area. So when it happens, the die temperature can increase significantly, and also we have to deal with a larger temperature gradient inside the 3D stack. So that's quite some challenge there. And for future technologies, we are looking at hybrid bonding, something like that, to further scale the interconnect density and power efficiency. And then let's look at the new dimension, which is scalability. Co-EMIP is a technology, actually it essentially combines EMIP and Foveros. The co-EMIP enables dense interconnect on the same package between different 3D Foveros die stacks. And ODI, which stands for omnidirectional interconnect, is a new technology which will offer greater flexibility when it comes to heterogeneous integration. It enables large top chiplets than the bottom chiplets. It can also be used to cantilever the chiplets if you want to. And they have these larger copper pillars connect from top chiplets to substrate. This provides robust power delivery and high-speed I/O connection. So the co-EMIP technology like co-EMIP and ODI offers great flexibility when it comes to package size, because now you can easily enable larger reinforced reticle die size package. And then you can also integrate quite different components on the same package. So those are very nice features, but there is a challenge that comes with it. One of them we are particularly interested as a thermal engineer is the thermo-mechanical enabling. How do we have a design and enable the loading and thermal solution to make sure we have a good quality thermal performance, especially the thermal interface material that will be touch the closer to the heat source, and how do we ensure that performance does not degrade over the lifetime cycle of the products. So those are the challenges. Yeah, so to summary, heterogeneous integration does offer a lot of benefits. And if we take a closer look at what the heterogeneous integration means. So this is an example use EMIP technology to integrate high-speed I/O chiplets and high bandwidth memory on the same package. This showcase. So in this package example, it has chiplets from 3 different foundries and six different process nodes. It's a showcase that this mix and match approach is feasible with standardized interface, right? So the benefit is very obvious because through this heterogeneous integration, we can integrate components of device IP optimized on different processes and to enhance the functionality of the package. And another driver is the need for high bandwidth memory with low power interface. And in addition, through the heterogeneous integration, we can take advantage of the yield improvement and shorter to time market by using smaller chiplet size from the next generation silicon node. So all these are very attractive benefits of heterogeneous integration, but it does bring a lot of thermal challenges. So when you look at the thermal challenges of heterogeneous packaging, first thing we have to look at is the source of all the thermal problem. which is the heat generated inside the chiplets. The performance CAGR and the integration of more chiplets on a package is driving the total package power to be higher and higher. And in the meanwhile, the power density also increase, especially when we move to use more advanced silicon nodes. Usually that associate when you shrink the silicon area, you have to deal with the higher power density. And then the 3D stacking can accelerate those increase in power density. This is because, as I mentioned briefly in the previous slide, it's when you vertically stacking chiplets, if they have higher power density IPs, and if they are vertically aligned, your effective power density in the same silicon footprint area will increase significantly. So that will end up with higher die temperature and larger temperature gradient. So that's, in summary, the heat source we have to deal with as thermal engineer is not slowing down. That power density, power increase, we don't see it slow down. On the other side, let's look at the heat dissipation. I will use in the 3D as an example. Each time when we're stacking chiplets vertically, that introduce additional interfaces. More interface means more somewhat contact resistance. And the material used between the chiplets are like interconnect and underfill epoxy material. Those material usually have less thermal conductivities than silicon. So we have to deal with a much higher conduction thermal resistance, especially for the chiplets at the bottom of the package. So it's we have increased power source, increased package thermal resistance. And in the meanwhile, by integrating multiple components on the same package, you may end up have to deal with thermal crosstalk. This means the heat generated by the neighboring chiplets can heat up your surface. This could be your heat spreader. It could be through the silicon interposer. If you are using silicon interposer technology, you can also have heat thermal crosstalk through that. Or if you see, I would just simply remove the lid, fine, and then you will have heat sink. Especially those high performance heat sink, they use copper. Copper is a fantastic heat spreader material. The base plate of the heat sink will also provide the path for the thermal crosstalk. This chart showing the impact of crosstalk. So when we plot the cooling capability, for example, you have two die in the same package, and you plot the die 1 cooling capability versus the die 2 power, you will see the die 1 cooling capability will drop as your power from the die 2 continue to increase. And obviously, if the slope, then the slope indicates the intensity of the thermal crosstalk. And also this chart also showing for the same design, if you have a 3D stacking, usually the cooling capability is lower. It's because of the increased package thermal resistance. So that's the crosstalk part. And in some applications, you may want to avoid that thermal crosstalk by including thermal isolation. This is because this leads to our next item is there may be different die junction temperature requirements for different functional IC, right? Because the heterogeneous packaging now opens quite significant opportunities to integrate different packaging and die and components on the same package. They don't necessarily have the same TJ requirement. For example, photonics IC, they are very sensitive to temperature and temperature swings, and the associated thermo-mechanical stress come with that. And then memory is another example. Memory performance is very sensitive to memory die temperature. It's not so that's why it's common. You will see when you purchase the memory, the vendor will tell you the design temperature based on you want 1x refresh or 2x refresh, right? So when that happens, have some sort of thermal isolation to provide some protection for those components from heating, thermal crosstalk from other high components will help you to be able to reach better performance. And then the last one is thermo-mechanical enabling. I think Gamma has given a very comprehensive review in his Tuesday keynote speaking. So I will encourage you to go through his presentation to get a little bit more inside information. But high level, when we are dealing with large packages with different components integrated, the first thing is your thermal interface material that touch the close to the heat source. That is the key, and that's not easy when you deal with heterogeneous packagings because the larger form factor, the dynamic warpage, and also sometimes you have to deal with the silicon flat, silicon surface flatness, and also dealing with your team has to be able to bond with silicon. It could be mold between those silicon. You'll have good adhesion to both surfaces. And also another challenge is reliability. How do we make sure the team does not degrade over the life cycle of the products? Those are all part of the thermomechanical enabling challenges. Now, yeah,
we have a question.
sure.
So for the thermal crosstalk, it could be higher on the interposer, but with EMIT, it should be less. Now, the fact that both chiplet and the XPU are sitting on the substrate, independent heat flux may be higher through chiplet due to the high power density. Is this correct?
I didn't get the last one. Can you repeat it? You see when they sit on the substrate?
Since you have both the chiplet and XPU sitting on the substrate,
Yes.
the independent heat flux may be higher through the chiplet due to high power density of that stack. Is that right?
I don't. So I would say the power density is determined by your performance demand, right? So the XPU, whether it's XPU or HBM, so the heat flux is determined by your design, right? And but the impact of the heat thermal crosstalk, our observation is we expect to see more crosstalk if we use a silicon interposer, simply because silicon is a much better material when it comes to heat spreading compared to substrate. Does that answer your question?
So I'm not sure. So I'm not sure the person who sent the question. I'm not sure. Hopefully they'll reply to me. Go ahead and continue.
Yeah. Okay. Now
You said yes.
Okay, thanks. Now we move to looking at the power density, because that's the source of all thermal engineers' problem, is the power density. So first, I want to highlight it's not straightforward to come up with some power density trend. This is because those numbers are very dependent on architecture and the use case. This is just my speculation, considering both steady state and transient thermal need. What we are dealing with for the next few years, the power density range. So the purpose is to provide some guidance to thermal communities, so we can focus on developing technology building blocks to provide maximum and cost-effective cooling. That said, I do expect the average die power density will continue to increase year over year. And on top of that, we also need to handle the hotspots. If you look at power distribution over a die area, this is example. It's not going to be uniform. There will be peaks in some area. So we call those hotspots. So the hotspots is easily we have to deal with somewhere between 2 times to 4 times of the average power density. So we need some more technologies that can cover both the average power density and also the hotspot density. And it's very important to make sure we understand the upside capability of both 2D and 3D architectures. As I mentioned, emphasized in the previous slides, the 3D architectures usually associated with higher conduction thermal resistance, and you may not get the same cooling capability when you move to 3D architecture unless you have some unique or a niche thermal solution that is targeted at improvement for 3D architecture. I will give maybe one area that's kind of has raising some, we have seen some publication with proof of concept data. So that's the thermal demand part. Given the complexity of the thermal challenges, we need holistic thermal solutions. Yeah, thermal engineer, we cannot just say, okay, go design your cooling solution to handle much higher power. We need to go back to the source of the problem. I think a few presenters, speakers in this workshop, they have all mentioned similar concerns or problems. So if we look at a thermally aware design, these are temperature maps. The top one is the temperature distribution with uniform heating, and the bottom one is with non-uniform heating, is more realistic user conditions. If you look at maximum temperature, we call it TJ max, the non-uniform heating is much higher with than the uniform heating, and also obviously the temperature gradient is much larger compared to the uniform heating. So to convert that to power cooling capability, so that means in general we would like the power distribution to be close to uniform. So for the same, so we can cool more power with the same cooling solution under the same TJ spec. We have used this approach for CPU for many years, right? It's a transition from single core to multi-core architectures. So but nowadays, if you look at all possible IPs can be integrated on the package. Some IPs, their power density are increased very fast. And those are area I think the community need to work together to get the thermal awareness in the design from the beginning. It cannot be just trying to fix that problem after the design, the circuitry design is completed. Then you will lose a big chance to improve the thermal. And through the improve of thermal, you can actually get more electrical performance, silicon performance from the device. Then the second area is a package thermal improvement. We observed in the last 1 to 2 decades, the package thermal resistance has decreased quite significantly, generation over generation. We want this resistance to be as low as possible to be able to cool more power. Then cooling solutions. The innovation in heat pipe and vapor chamber has extended the air cooling capability significantly. In the meanwhile, we also see increased application of liquid cooling. This include both cold plate liquid cooling and immersion cooling. So next, I'm going to give you an example of thermally aware design. And then I will switch to the update from the Heterogeneous Integration Roadmap thermal trick update because they have a more comprehensive view of these two areas. So give you an example using FBGA. This is the transceiver die. And if you look at the different programming, it's obviously different programming can affect your power density distribution significantly, given this is you use all the banks, use every other banks, right? And then when at scenario, when you do have a choice to influence the configuration, on the right, you see an example of 8 channels. And if we see, okay, we have the option of this A, B, C, D, 4 configurations, by instinct, we will know, okay, configuration D, which is the least lumped one, will give you the best thermal result. So this is validated by the lowest package thermal resistance, which is quantified by SciJC. So configuration D will give you the best performance. But in real applications, the design and configuration will be so complex. It's not easy just to take a look at the design and you can define. And then that's why it's very important to have the design tool to have the capability to evaluate the thermal impacts and optimize the design for the eventual goal of the best performance, not just for thermal, but all the silicon performance. At Intel, we developed a proprietary technique that can evaluate the thermal impacts and optimize the configuration to get better performance per watts. And we are building this capability in our Quarters tool to optimize our FPGA programming. So that's the example showing the importance and also effectiveness of thermally aware design. And now I'm going to move to the update for Heterogeneous Integration Roadmap. So this is under IEEE. Under the Heterogeneous Integration Roadmap, there are many technical working groups. Thermal working group is one of the working group. This is the working group I personally participate. This is a thermal effort kicked off in 2018 with 30 industry and university expert contributors. And then last year, we have about 10 more new members joined us. So the effort of this working group is to look at the problem that is prevalent in the industry, and heterogeneous integration becomes kind of the topic or theme of this thermal technical working group. We finished the first publishing back in 2019, and you should be able to find that chapter on EPS website. Since the first publish, we have received a lot of feedbacks from reviewers and our partnering technical working groups. Based on their feedbacks, we identify 6 more areas that we will focus on this year. These are hotspot thermal management, high bandwidth memory cooling, photonics thermal control, power and power density trend. I kind of touch base in today's presentation. Silicon microchannels manufacturing, and thermal test protocols for heterogeneous packages. So when we start working together, the first task we've completed is the canonical thermal problems associated with heterogeneous integration. So these 7 areas were identified. I kind of explain why we see thermal challenges that are relevant to the 2D chip with stacked memory, interposer, 3D stack die with conduction interfaces, and also a photonics-based heterogeneous package. For the interest of time, I'm just going to explain a little bit more details of the rest of the 4 area. One is the 3D stack die. I mentioned this many times in today's presentation, is the challenges come with 3D stack die. So one method that may work is embedded liquid cooling. I will explain a little bit more in the next slide. So this embedded liquid cooling is by cooling through a coolant flow either within the chips, it's called inter-chip, or between the chips with high power or high power density. And this has we see some proof of concept showing the benefit, but obviously it will come with a lot of challenges. Then another area which is quite important is harsh environment for military, aerospace, and automobile industry. Some electronic devices must meet very stringent requirements to operate safety critical operations in extreme temperature, uh, dust, vibration, even corrosive environment for a period of 10 to 30 years. It's very stringent requirement when it comes to reliability. And also in automotive industry, uh, burn-in and test of heterogeneous packaging or multi-chip packaging is particularly challenge. It's kind of a no issue in the industry. And when it comes to a mobile application, we see continuous shrinking in the package form factors. That in conjunction with in significantly enhanced power and functionality in this area is making has bring in significant thermal challenges. And one typical thermal solution in this area is using micro heat spreader, micro heat pipe spreader to touch the surfaces of multiple components or devices on the same PCB to promote the heat spreading. So that's a very common solutions in this space area. And then last one is voltage regulation. That's a steady and gradual trend to move to lower threshold voltage regulations. And that is driving the package level current to be higher and higher. The trend is looking at several hundred of amps. One possible power device that can be heterogeneous integrate on the package is voltage regulators. And then this voltage regulator will become the potential hotspot in the package and may bring a significant thermal challenges. So those are the canonical thermal problems. The thermal tweak sink will be is prevalent. We see very common in the industry. And then what's the solution path, right? And then we identify several advanced technologies and research. The first one is thermal interface materials. We need a material which gives us low thermal resistance. The thermal resistance include both contact resistance and the bulk resistance, the material resistance. We need high mechanical compliance because of the warpage challenge and the large form factor challenge. And also, we want a minimum team performance degradation of the life cycle of the products. So those will be three, in my opinion, the three key performance metrics to quantify a good thermal interface material. Then the second area is the team come looking at the available thermal solutions and what's the system thermal limits for high performance computing multi-chip modules. At high level, we see about up to 100 watts per centimeter square cooling capability using air cooling with vapor chamber. If you can move to liquid cooling, we see about close to 500 watts per centimeter square for direct water jet impingement. This is a single phase liquid cooling. And then the ultimate cooling limits seems to be close to 800 watts per centimeter square of using direct water cooling with silicon microchannels. That's the paper published back in 1981 by Tuckman. So those are kind of the system limit. And then also want to talk about a little bit the embedded liquid cooling. There are a few research kind of paper published in the last several years on the concept of embedded liquid cooling to cool chip stacks. All of them are based on the concept of a two-phase chip level cooling. There's a paper by from IBM looking at the intra-chip cooler by introduce the coolant in within the chips with high power density. They reported 350 watts per centimeter square capability. And then a paper by Purdue looking at, they call it manifold micro channels. Those are very small micro channel, narrow and high aspect ratio micro channels. They reported over 1,000 watts per centimeter square cooling capability. And a paper from Stanford looking at also small scale two-phase on-chip cooling also achieved greater than 1,000 watts per centimeter square. I think this paper, they demonstrate on very small silicon area. And those are looking very kind of exotic cooling solutions. Can any one of those be a niche solution? I don't know. Please share your thoughts with me. Personally, I do see there's a lot of work need to be done when it comes to real applications. And then advanced thermal material, as mentioned, 3D stack is become a challenge. We need a material for interface and underfield material to improve the heat spread. And the last area is thermo-mechanical modeling. As we mentioned, thermo-mechanical enabling is going to be very challenging. We need the right tools, framework, and flows to be able to model and design and optimize your packaging at both the die and the packaging level to look at those thermomechanical effects. So those are the technology and research the team was looking at, we think is important to mitigate the thermal challenges. And finally, I'd like to wrap up my presentation with a call for innovation on thermal management in this specified, especially in this area. The first one is better teams. We would like to propose a near-term target of 2.5x RGC reduction. And for the next decade, looking at 10x reduction. And for your reference, today we have capability of about 0.1 to 0.2 RGC capability. And the second area is dual-purposed teams as a warpage control. Warpage has become very coupled when it comes to the team performance. So have team with also some warpage control will help mitigate those issues. And then the next one is complement package level solutions with system level solutions. We need research in liquid cooling, material and design options, including immersion cooling. And the next, the new material and cooling technology to improve the heat conduction. This is specifically, particularly important for 3D die stack. Especially also, we need a new material to be able to mitigate hotspots. We also need to improve metrology. I didn't talk about this, but this is also very important area. So when we move to these very complex packages, does our current metrology able to meet all the requirements when it comes to thermomechanical characterization of the package, right? Well, some of the technology may need a new investment on new metrologies. And then increase the focus on transient responses. I believe transient response is also one of the key areas for the test community. We see multiple speakers mention that challenges. And in end user condition, this also could be challenging for some workload. And strengthening the co-design interfaces. I mentioned it's very important to have thermally aware design. So this is part of that. And then finally, we need to look at new technologies like photonics and quantum computing that are on the horizon. So with that, let's wrap up my presentation. Thank you for your time. I don't know if we have time for a few more questions.
Rob, this is Calvin. I do have a question.
Yes.
You bring up this is an excellent presentation. Thank you. I do have you bring up a interesting point, right? That in a multi-chip packaging, you have a different type of chip that had a different junction temperature requirements.
Yes.
So from a thermal management standpoint, how do you manage it and maintain the different junction temperature for different type of chip?
Yeah, so I touch base a little bit when I talk about the thermal crosstalk, right? And then some sort of a thermal isolation will definitely help. Another way is you also need to work with the device designer to understand the performance. And luckily for those packages, they are workloads that you will use. Let me go back to. There will be scenarios where you use XPU more, and then there'll be scenario use the memory more. One practice we observe in the industry sometimes, especially when you have silicon interposer, is if you run heavily loaded memory workload, sometimes they will actively monitor the load from the XPUs. So it does not overheat your memory to impact your performance. And another way is you have to look at your whole package component and or system thermal solution, see if you can balance your need from different components on the same package, right? So this will be your design. So if I draw another curve to look at the die-to cooling capability, it will be something like this, if you can see my mouse, and this will be your design space.
Mm.
Yeah.
See. Thank you.
You're welcome.
So there's one more question regarding the crosstalk. Is there really crosstalk that can have a positive, negative, random impacts, or is it more like additive? More heat is more heat.
Okay, so if this is more relative, right, compared to with the crosstalk without the crosstalk. As I mentioned, there are scenarios you may get benefit because if you are running workload, for example, the XPU power can be much lower. Now you have more heat spreading surface to take advantage, right? Or maybe because the HBM has much higher stack resistance, your XPU actually can benefit when your load, your thermal load on HBM is low, then you can take advantage of a bigger spreading surface to use that. But when you come to the workload, you need to have both components heavily loaded with high power. That's the time when you see this crosstalk will hurt the performance you are looking at. And typically we see the capability, like when you draw those curves, combined total power should be a little bit less when you have multiple chips integrated on the same package. Another reason is the team performance. When you dealing with much larger packages, usually it's just more challenge to achieve same team performance as a simple, smaller form factor single chip package. Yeah.
I also want to thank our sponsors once again for making this event possible: Advantest, Amcor, Indium, FormFactor, and Nidec SVTCL. Advantest is a global leader in the ATE industry with over 30,000 installed systems using nanotechnology products to support leading edge process nodes with a large global workforce over 50 countries, working in environmentally sound processes. Amcor, who's providing OSAT services with a focus on technology, quality, and service, certainly advanced packaging, quality first, and service from design and test through drop ship, using a global footprint from around the world, but with local sales and support. And Indium, the premier assembly materials designer and manufacturer of thermal interface materials, solder paste fluxes and preforms, and certainly metals and compounds to solve challenging thermal problems. So once again, I'd like to thank all the sponsors. When you have an opportunity, please thank them yourselves to encourage them to sponsor more great events like Too Hot to Test. And so thank you very much for joining us. And I wish you a good rest of your day and look forward to having you participate at a future MEPTEC event. Thank you.